Hello everyone, and hope everyone's enjoying the great conference. So welcome, and again, welcome to our session on performing Postgres, tuning performance using wait events. Now in this session, we'll be talking about utilizing wait events in Postgres SQL to identify and tune performance bottlenecks. And tracking wait events was basically added in Postgres 9.6, right? And prior to that, Postgres only provided information about the state of the session and if it was waiting on something. Now, this feature in 9.6 was one of the best observability features that was actually added to PostgreSQL. And we'll uncover how it actually helps DBAs better tune their database queries. But first, let's introduce ourselves.
Hi everyone. I'm Sameer. I'm a database specialist at AWS.
And hi everyone, my name is Roneel Kumar. I'm a database specialist also with AWS, based out of Sydney, Australia. Now, we will be talking about how to monitor the slow queries on Postgres databases and some of the common locks and how to monitor sessions and sample for them. And then finally, some of the common wait events and how to actually go about mitigating them. Now, as you can see, from our agenda, we've got a few concepts and examples to cover. So in the interest of time, we'll actually take questions right at the end, if it's possible. Now, when we look at monitoring and how to tune them, this may sound a bit daunting to begin with. Now, and this is because there are different components in a database that you actually need to go, monitor for, which is applicable irrespective of where you're running your database, be it on the cloud, on-premises, or wherever. And it involves the underlying infrastructure, operating system, and most importantly, your workload. And additionally, when you want to be, you want to be aware of the critical events that are actually happening in your database, such as the slow queries, auto vacuum, and checkpointing. And there are two common ways you can go about monitoring your slow queries. So the first one involves logging your slow queries by setting logmin duration statement to a threshold. It is a dynamic parameter which only needs a config reload of the Postgres config file. The other approach is to actually use what's called PGStat statements extension, and it provides a view into your average and maximum time taken to execute top SQL statements. And PGStat statements also provides other useful information about the SQLs that are running, like your buffer hits, disk read requests rather, temporary file usage by the queries. And enabling PGStat statements requires an update to the shared preload libraries parameter and creating the extension on the respective database as well. Now, your workload can typically get bottlenecked by things like CPU, I/O, or lock waits. And a typical example of CPU-bound workload is the ones with high concurrency and working sets fitting inside the shared buffers. Whereas for I/O, you will have where the most common bottleneck is the working set does not actually fit in memory, or where checkpoints are unable to keep up with the write activity. And you can also have workloads where you'll have contention, such as workload where there's a small set of buffers that are actually getting modified by concurrent backends, or even lock contention for a hot row or a hot page. So while SQL monitoring techniques we covered gives information about the resource usage and the time it takes to execute, they don't really point out if there is a contention on the resources. Two bad queries causing this I/O could run in completely separate time windows, meaning they'll never contend. However, if they were actually running at the same time, this would cause a performance drag. So one will have to know the workload and ensure the monitoring that you're setting up and the sampling that you're doing for these metrics are done at the right intervals, and you're collecting the right data in order to actually sample for them. Now, looking at the PGStat activity view, it actually gives you a current state of each backend process along with with a query that's executing it. And and with that, the age of the query and the related transactions. It will also provide you information about the wait events, right? That is basically what resources is the query actually waiting on, such as your I/O, your locks, or your lightweight locks as well. And it lets you look at the state and wait events. We'll actually go through and look at the wait events and state actually in a bit more detail later as well. So actually, let's cover session state first. So a backend, it's basically where we've got a backend process. It can be in different states, and the most common ones are either active or idle. And it is common to see, the connections to be in idle state, even when you're actually using tools like a connection pooler. So in all this, but the one that actually causes the performance issues the most is the idling transaction. And this is typically because if you've got an application bug, or when you've got things like non-database tasks that are actually calling, for example, a third-party API, or you're sending updates to message queue that are actually getting performed in a database transaction. So our session in these states will actually hold on to the locks until the transaction is actually explicitly either committed or rolled back. And it also holds onto the xmin ID of that session, and it actually ends up blocking auto vacuum. So that in turn will actually cause performance issues like your high I/O, you've got poor buffer utilization, as well as things like increases of wraparound as well. Now, with that, let's cover wait event type. It actually provides you information on the nature of the event, right? So, for example, the details of the resource that the session is actually waiting on is indicated in the wait event column. Now, a session in active state can actually go through different wait events as the query progresses. For example, a wait query, as an example, might be waiting for example, on a data file read to read data from storage, and then it actually may go in and wait for example, a lightweight lock on buffer, or a buffer pin lock before it can actually go in and modify it. So whilst committing the update, the session will actually go in and wait for a lightweight lock on a well insert again then. Or if it's the only process running, then it doesn't actually have to go in and wait on anything. So it'll just go in and complete itself. But typical wait event times that actually cause contention is of type I/O, locks, and lightweight locks. And we'll cover these in our examples later as we go through a troubleshooting scenario as well. Now, Postgres uses different types of locks to protect against concurrent modification to actually give to a given resource, in fact, and by multiple backend processes. And the backend processes wanting to access a particular resource will first require a lock, like calling dibs on it. But if another process already has that lock, it will add itself to the wait queue and try to acquire the lock again in a loop until it finally acquires it. Now, Postgres uses spin locks for executing CPU instruction to change an atomic variable. Now, then there is lightweight locks, which are actually acquired for a short period of time. And when working on data structures in memory, for example, when performing, like well insert to buffers. But there's also other lightweight locks that you will actually see that are there to protect against concurrent I/O for certain files, such as like commit logs. And then you'll have your heavyweight locks, which are used for protecting your SQL objects like tables or indexes against concurrent access. And Postgres uses multi-version concurrency control to reduce the locks needed, but we cannot completely do away with locking as well. For example, you can still have a select of sum of all account balances whilst there's concurrent updates to, for example, updates to debit and credit your account, right? But if you've actually got a select query running, you can't go in and alter the schema definition of the table because locks are required. Locks basically that are required are incompatible, right? And again, you will have buffer pinning that's actually used to indicate that a specific page in buffer is actually being used by a backend and it can't be removed. Now that we've actually talked about our event types and log types, let's see how concurrency typically affects performance as well. Now, if you've got high concurrent workloads with several hundred or thousands of active sessions, it'll end up affecting your resource utilization. And you can typically observe it at the operating system level, either in the form of I/O latency, or drop in your freeable memory, or increase in your CPU utilization. Now, here's an example that we actually have of how an increase in the active sessions can actually end up affecting your CPU utilization. But what's really leading up to that high CPU utilization remains kind of a mystery. And that's why you need to use a tool like, for example, a view like PGStatActivity to sample and understand what's really going on in your database. Now, with that, I'll actually hand over to Sameer to actually go through a scenario.
Hey, thanks, Roneel. Thanks for setting up that context about how the logs work and what kind of logs Postgres has, and a run through of PGStatActivity. Now, when you're looking at a performance issue where you have high CPU utilization, looking at PGStatActivity in that moment is not going to help you troubleshoot that problem or identify what is causing that problem. You'll have to look at historic data. You will have to look at everything that has led up to that moment when that performance crisis kind of bubbled up and is causing an outage or is causing a significant performance drag that is now visible to your end users. So that's why you would need to look at identifying those or sampling data about what's causing performance issue. Now, when you're looking at tuning your workload, one of the ways to do that is to look at slow running queries. There are two ways to go about that. One is you could log slow running queries, and the other approach could be to log all your queries. Now, both of them have some drawback. If you're logging only slow running query, it may not point out queries which are taking most amount of resource. For example, a query that takes 100 seconds or 500 seconds, but runs only once in every few hours, or maybe just once in a day, that's not the most resource consuming query. But the query that is running every second in hundreds of connections and taking 100 milliseconds each time, that is the query where you need to put your tuning efforts if you're trying to identify a bottleneck. And you miss that data point because this query is not slow enough to be logged. And then the challenge with logging all your queries, well, if you log all your queries and you also log lock weights and duration of the queries, that is kind of quite comprehensive information that can get you started when you're working on these problems. But that is not without adding an extra performance drag on your production server, because every time you're running a query, there's an extra time spent logging it to the server log. So let me present a different idea here. An alternative to that is to sample sessions, which is essentially sampling PGStatActivity. Now, what you see here is 4 different access patterns. One of them has a long-running query, a single user environment. The second one is a multi-user environment, but 2 moderately long-running queries. And the third one is a set of short-running queries which are getting captured by different sampling intervals. And all of them, if you look at them and summarize them, you get one active session. If I look at them and try to summarize how many active sessions I have throughout my sampling history, I'll get one active session, right? That's what sampling does. Now, the view you will get by combining these different snapshots is a lot like rendering maps. When you zoom in, you will get the slow running queries. But as you start zooming out, and as you're looking at a big picture at a longer interval, you will get to see those queries which are causing most amount of resource utilization, even if they are running relatively faster. And the one single query that ran only once throughout a history of, let's say, 1 hour window, that will get averaged out. That will get missed out. And when we talk about sampling, one thing that pops up is how often should you sample? Now, typically 1 second is a good interval to take samples, and that is going to give you a pretty good understanding of the activity that is happening on your production server. well, you may have queries that is taking just a few milliseconds or a few hundred milliseconds. But if they are running only at an interval of several minutes, that's not the query you would want to start with when you're troubleshooting performance issues. That is not going to be the query of interest for you. But if a query is running in a few milliseconds, but it runs in 100 sessions and runs pretty much every second, that's the query that will get captured even with 1 second sampling. You will be able to capture that query in some or the other session, in some or the other sample. And of course, if you have, if you have a long-running query, then that long-running query is going to get captured in pretty much all the samples. Now, when you take these samples and you put them out as activity, it gives you an acute view of what is happening on the database server. Now, what they give you is a snapshot. Instead of adding up all the statistics to a point in time, they give you a view of that point in time. This is very different from what you see with other PostgreSQL statistic view. Like if you look at PGStat statements, it gives you a view of up to that time, like how many rows were fetched or how many times that query was executed. You get that kind of view from views like PGStat statement. It gives you quantities about query. It gives you statistics up to that time. But when you're sampling, it is not giving you quantities. It is rather giving you a view of the system at that point of time. Now, what you could do is, when you're getting each snapshot and a view of the system, you could also average them out over a period of time. So you could say, let's try to find out what is the average activity for a 10-second window. And if you have 2 user sessions and 10 samples, out of which only you found activity in 5 of them, and if you try and average that, you will get 1 average active session. So we are looking at now average activity, not activity, but average activity for a given time period. And as you start zooming out, this activity also starts getting averaged out. So the noise starts getting filtered out, and you will be able to see those queries where you should be focusing your tuning effort. Now, if you look at just the average activity, it's a good measure of how busy is your system. Is your average active sessions 1 or 10 or 50 or 100? That's what it tells you. But it does not tell you whether your workload is CPU bound, or is your workload IO bound, or is it mostly waiting for lock waits. To get that perspective, you could also include state of the session or the resource it is using when you're sampling them. And then that gives you a view where you can see average active sessions by the session state. Now you get to understand whether your workload is CPU bound, or your workload is IO bound, or is it mostly waiting for lock waits or something else. Yeah. Now, let's try and expand that view and include PostgreSQL wait events that Roneel just talked about. So when you extrapolate that view, that same concept that I talked about, to PostgreSQL wait events, you get a view like this, where you can see in your workload, what are the top wait events? What resources are typically bottlenecking your workload? In addition to capturing the query state, if you also capture the query itself, then you also get to understand what is the top contributor to your workload. Which query is the top contributor to your workload? And then because you have captured queries and the wait events, both of them, you can also create a pivot view where you can see which particular wait events are mostly affecting, or what queries are in which wait events most of the time. So you get that pivot view as well if you combine that data with a different perspective. And then you can also sample other PostgreSQL views like PGStat statements. So one information that you don't get in sampling PGStat activity, that is those quantities, now you can get that as well. So you can also correlate your top queries, their wait events, along with these quantities, like how often is this query running, how many calls happen in that particular time. Because you're taking samples of pgstat statements, you can do delta between them, and you can get this cross correlation as well. Now, earlier, this was not straightforward or easy to correlate pgstat statement and the samples from pgstat activity, because you have to do a rough calculation between which to match the queries. But in version 14, a concept called query ID was introduced in PostgreSQL, and you can configure PostgreSQL to compute that automatically using pgstat statements module. So you get to correlate much easily now. Now, if I put all of that together that we have talked about, if you put all of that together, you will be able to see average activity by the wait events, what are the top SQLs, and you will also be able to see which are the wait events typically bottlenecking these SQL statements, and then SQL statistics as well. Now that I have talked about how you can use wait events, how you can capture that data, how you can build a view of your workload, let us talk about a scenario, a troubleshooting scenario. We have built this hypothetical scenario using a custom workload running in PG Bench. We are running a synthetic workload where we have used our own queries to just produce some bottlenecks. But it's quite similar to some of the workloads and some of the wait events that we have seen among users as well. So I'm going to invite Roneel back into the conversation to just walk us through this scenario. All right. So Roneel, tell me what was the first thing that was reported to you?
So the first thing that we kind of saw was there was high load on the server, and we saw kind of the number of database or number of actual processes on the underlying operating system was showing between 100 and 200.
Okay, so what about the workload? What changed in the workload?
Well, Matt, nothing has changed. It's the same workload. Access patterns are same as earlier.
Okay, tell me a little bit more about the access patterns.
Well, the application collects events from sensors, which actually inserted into our events table, and then there's another process that updates the events after analyzing if the event metrics, such as temperature, moisture, are aligned with the trends, and if there's a discrepancy, it actually logs it to the tables as well. Okay,
and what kind of data types and indexes are there?
Okay, so the event data is actually stored in a JSONB column, and if there is a deviation from the trend that's detected, then it actually goes in and is included in another JSONB column, and there's a primary key, and there's 3 indexes, two of which are expression-based JSONB operators as well.
Okay. So basically nothing has changed, so you don't have really a point in time to start with. You just know that a certain performance problem started happening all of a sudden. So how did you start your investigation?
Well, the first thing we reviewed here is the active sessions and see if it's actually affecting our CPU utilization. And what we see here is even though the CPU utilization has increased, the active sessions have rather reduced over the 5-minute period.
Okay. Okay, so the activity has not increased so much, but there is still high CPU utilization. Okay, so what's the next thing you looked at?
Well, we actually went in and looked at our performance insights metrics tool, which is available on Amazon RDS, and it actually gives you a slice of the average of active sessions by wait events. But we'll actually not talk about performance insights in detail. It's basically samples PGStat activity every second. And we'll come back to this view and deep dive on it later. But let's first try and understand some of the wait events that are actually in this workload, okay. Sameer.
Let's go ahead.
Okay, Sameer, help me understand some of these waits. Like we've actually got the client read wait that we're actually seeing here. I've seen this often in my PG Bench test. So what are these?
Yeah, this client read wait event, it typically comes up when you have an increase in latency between application and your database. Application as in whatever client that you're using. So if you see an increase in this, it is likely that the network latency has changed, or the application server itself is overwhelmed and it's not able to allocate resources to the application process that is holding database connection. So it might, it seems a little bit unnatural that we're talking about a database wait event, but in order to look at this one and analyze in detail, you have to go and look at the application server and its utilization. You talked about PG bench. Yes, it does come up often in PG bench tests, and typically that happens when you have very few threads of PG bench. So there is a thread parameter in PG bench test, and there is a connection parameter. The thread parameter is how many threads are going to run on the PG bench client. And if you have very few of them trying to manage too many database connections and send data over them, you can see this wait event come up in that test.
Okay, interesting. But you mentioned connections, but we've actually seen this actually come up often in our even when you're using a PG bouncer as well. So why is that?
Yeah, if you see this wait event come up in your PG bouncer, in your workload, which is using PG bouncer for connection pooling, it is likely that you're sending query packets which are larger than 4 kilobytes. And in that case, PG bouncer gives parameters. It's a low-level network parameter that you can tune. It's called PKT buff, PKT underscore buff. And you can tune that to minimize this.
Okay, interesting. Is there any other scenario that will actually cause this wait time?
Yeah, if you have a copy operation that is sending a lot of data to the database server, in that case also database server might be waiting for all that data, and it will show up as client read wait event. Also, if you have transactions, or rather sessions, which are idle in transaction state and waiting for the client to send next set of SQL statements, even in that case, you'll see this wait event go up.
I know this one actually. It's basically when the increase in the wait event is because it indicates an increase in I/O. So, what typically are the reasons for this?
Well, typical reasons are scenarios like where your data volume has increased. So even though your workload has not changed, the amount of data, the number of rows in tables has increased, or there is a query that is not using indexes, or there are multiple queries not using indexes. But something that often gets overlooked when you're looking at this wait event is bloated tables. So that can also lead to this wait event go up.
Interesting. So how does one mitigate for this?
To mitigate this, the first thing you would want to look at is queries that are not using indexes, tune those queries, introduce indexes where necessary, drop unused indexes, manage bloats in your tables. You can also look at partitioning, so those things would help. You can also increase the instance or the amount of memory available. You can go to a bigger box, get more resources, that will also help. But workload tuning should be the first step, I think.
Thank you. Now, going on to this block extend wait time. So I've actually seen this come up often when I'm running insert-only workloads. Yeah,
this is a wait event that comes up when your backend, Postgres backend process is waiting for the data file to be expanded or extended. When there is a new coming row version or a row and that cannot fit inside the data pages that are already there, it has to be extended. Now, typically PostgreSQL will take a little bit of an aggressive approach to expand the data files so that it can meet the future growth requirement as well, so that it doesn't have to keep extending every now and then. But if a workload is predominantly just inserts, then you're likely to see this wait event come up. You can also see this wait event come up when you have modified, in fact, reduced the fill factor. That can also increase this wait event.
Okay, interesting. But in our scenario, it's basically a combination of inserts and updates.
Yeah, so if you have inserts and updates happening, you're likely to see some dead rows getting created, and these dead rows will get cleaned up. So you would hope that some of the inserts will go and take up the space cleaned up from the dead rows. And if that is not happening, then likely either auto vacuum is not running, or it's not able to keep up with the workload you have.
Okay, so how do you mitigate for this?
One of the things that you could do is first go and look at fill factor. Make sure that nobody has reduced the fill factor or you're not using a non-default fill factor. You should also take a look at dead rows. You can look at pgstat user tables to identify if a table has too many dead rows, and then reduce the amount of bloats you have got there. Also tune auto vacuum if you could. There was a session by Robert earlier.
Thank you. Okay, cool. So this one seems to be related to memory. So why would there be a contention of buffer content?
Yeah, okay. Let's take a step back. Let's try and understand how PostgreSQL uses memory. Any kind of read or modification that has to be done by the backend process, it will always happen in buffer college, therefore as shared buffers. So first the backend process will wait for an IO to be, for the file to be read if it's not already in buffer, and then only the modification can happen. Now the buffer page has got two components. One is a buffer descriptor, which is basically metadata about the buffer, and the second is buffer content. The buffer content is where the data actually sits. It's read from the IO process. Now this event comes up when a session that is trying to read or write to a buffer, but it is waiting for another session that has locked that same buffer to modify it. That's when you would see this wait event come up. You can also see this when there is contention of data, or rather pages, in a highly concurrent workload or in large data sets.
Okay, so how do you actually go about typically reducing this wait time in your workload?
So some of the ways to minimize this lightweight lock on buffer content involves reducing your working set and ensuring that it can fit inside the buffer cache, such as partitioning. You can also look at reducing the concurrency, number of sessions working at the same time, reducing the concurrency so that there is less concurrent access to the same buffer page.
Okay, this one also looks like is related to buffer as well. So how is this different from the previous one?
Referring back to what we talked about just now, there are two components, buffer descriptor and buffer content. The content is where the data is. This wait event occurs when a session is waiting to associate a data block that is on disk, which has been read, with a shared buffer in your buffer pool. That's when this wait event comes up.
Okay, so why will I see an increase in this wait event then, like over time?
Yeah, an increase in occurrence of this wait event is going to happen when your workload has working set, that is frequently accessed pages, which are not able to fit inside memory. So there are often pages read from the storage into the memory, and they are getting flushed out because somebody else needs that page, and then you have to read that page again. So that's when this contention shows up. It can happen momentarily in some cases. For example, when you have added a new index. So when you add a new index, your queries are trying to use that index now, so the index pages will be loaded up in the memory. And you will see this wait event come up. But that will be for a short period of time, and you can validate that by looking at statistics from PGStat database or PGStat statements. You will see the buffer page reads increase, shared page reads increase at that point of time. But like I said, if it is momentary, then you should see another pattern just after that increase. You should see that shared buffer hits would increase, and that's an indicator that this wait event should not appear anymore.
Okay, cool. So is there anything else that will cause a sustained increase like that? And how does one mitigate for this then?
Yeah, a sustained increase that has happened over the last few days or over a few months indicates that you might have bloated tables or bloated indexes, because they cause a reduced efficiency of buffer cache. So you're now reading and reading more pages to satisfy same queries because the data is spread out because of bloats. Basically, to fix this, you could increase the amount of memory available. Of course, you can move to a bigger box, but you should also go and investigate bloats in your database and bloats in your tables and indexes both. Adding right kind of indexes, dropping unused indexes, they will also help.
Cool, awesome, thank you.
Okay. Okay, now let me switch it back to you, Ronil. What I see here is a lightweight lock, but on wall. Aren't wall files written on every commit? And that should be I/O related. Why is this a lightweight lock?
Yeah, great question. So, whilst performing writes, the Postgres backend actually needs to insert well data into the buffers, which is then in turn written to the well files, right? So, to protect the buffers from concurrent backends, Postgres uses what's called lightweight locks. And this wait event actually indicates that the backend process, in fact, is actually waiting to acquire that lightweight lock on the buffers too, and then go in and insert into the well data.
Interesting to know how things work internally. How do you typically mitigate this increase in this wait event?
Well, if you actually see contention on well insert, you should actually consider reducing concurrency or batching inserts, basically.
Okay, so another wall-related wait event here. How is this one different from the wall insert?
Yeah, cool. So this lock is actually acquired by the Postgres processes whilst the well records are actually flushed to disk or during a well segment switch.
Okay. Yeah, now that you mentioned that, I remember I've seen some users being able to mitigate this wait event by switching off synchronous commit or by even switching off full page writes. What are your thoughts on that?
No, bro. So switching off synchronous commit actually removes the waits for disk flush immediately, after the commit. But disabling and also the full page writes reduces the amount of data to flush. But both of these parameters actually should be, altered with caution, because this can either cause data loss or even data corruption. So instead, I would instead suggest kind of batching your transactions. In fact.
Oh, okay. Thanks for sharing that. All right. What about this one here? It's IPC related. Can you explain this one?
Okay. So this wait event actually indicates that the backend process is waiting for the reader group, the group leader rather, to actually update the transaction status at the end of a concurrent operation. But if the active sessions waiting on exec group update increase significantly, this could be because of increase in concurrency, changes to parameters that actually affect your I/O operations, or some issues with either the underlying infrastructure or the operating system.
Okay. This also got group in its name and is an IPC related wait event. Is this also related to group leader concept?
Well, yeah, this wait event actually indicates that the backend is actually waiting for the group leader to actually clear the transaction ID during the concurrent operations. The difference here being that one is actually waiting for the group leader to actually update the transaction status at the end of a concurrent operation, whilst the other is actually trying to clear the transaction ID.
Okay, thanks for explaining that. And now that we have covered the wait events and we have learned about how different wait events affect your performance and how you can mitigate them, let's bring back the performance insights view again, Ronil. And can you help us identify what's the top wait event here?
Cool. So, so if you actually go back to our view, we started with and if you review the metrics we see now, we see that the well writes kind of was the top wait event prior to our issue as well. And if you actually see, it's roughly about 80% of the waits that are actually there.
Okay, but isn't that expected from a write-heavy workload that is like ours? That does not explain the performance degradation that happened suddenly. So that brings me back to the question that I asked you earlier. What had really changed? Did something change?
Well, when we slice the top sequels by wait event, we actually see that the insert was actually more waiting on the lightweight lock for buffer content. And if you look closer, you'll see there's that the insert is now actually waiting for the lock extend wait type as well, which did not happen earlier. So if you actually look at before the event and during the degradation, there's a new wait type that's actually been introduced during this time as well.
Okay. Could you identify which buffer or what was the content of that buffer which was under contention?
So today, the wait events framework in Postgres does not actually help identify which buffer page or was the point of contention or what was specifically in that buffer to begin with as well. So, and again, one more thing you've kind of mentioned earlier is like an increase in buffer content is usually because of a increase in working set. So especially when we have actually concurrent write workloads as well.
Okay. Okay. So did you review any kind of I/O matrix or I/O activity?
Well, we reviewed the statistics of the background writer and checkpoints, and the information is actually available in the pgstat bg writer view as well. And just like other database and object level statistics, you can go in and sample this as well. So Sameer, can you help me explain the observations here?
Okay. Thanks for asking. What is apparent here, very clear here, is that the checkpoints are not happening because they are timed or because it's reaching checkpoint timeout. The checkpoints are being forced or requested because we are reaching the max wall size threshold. And when you look at that, the first instinct I had is maybe we should increase the max wall size and reduce the frequency of checkpoints. But then we also look at buffers which are written down by the backends. And if you look at that, despite having these forced checkpoints, there are still a significant amount of buffers that are being written down by the backend processes, which is kind of explaining why we saw the buffer mapping wait event or even the buffer content wait event.
So how does one resolve for this?
So one of the ways, of course, I mentioned this earlier as well, go to a bigger box. That will solve your problem because you will have more memory available and you'll have more resources to use. For RDS, you can simply do a click, go from 4x large to x large to 24x large. But should that be the first response here? What are your thoughts, Roneel?
Well, scaling may help resolve the issue, but you ideally actually want to get to the bottom of the problem, right? So there is obviously more work that needs to be done here in terms of tuning the workload itself.
So what kind of things you mean? What kind of things should one be looking at?
So tuning auto vacuum will be kind of the first step here, but then there is other areas that will actually help improve performance, right? So to improve concurrency, you can go in and use a connection pool or use a database connection pool like PG Bouncer. Now, if you're actually using Postgres on Amazon RDS, you can easily integrate with RDS proxy in the mix as well.
What would you suggest somebody who has a workload which is similar to the kind of workload and access patterns we have, where we have kind of a write-heavy workload, a lot of updates, inserts happening, and the data that is there is predominantly time series kind of data? Well,
you can experiment with reducing the fill factor. It can also help with buffer contention as well. But it will increase the buffers needed to actually keep the working set in memory. But if the data is actually time series in nature, you can just go in and easily partition the table then to ensure that the most recent data actually stays in memory.
Okay. Any other advice or ideas you have?
So you could actually go in and drop indexes, but also see if there's an opportunity to actually combine a few of them, or you could go in and drop seldomly used indexes as well.
Okay. Okay. So yeah, thanks for this conversation, Roneel. Now I'll hand it back to you to summarize this that we have covered today.
Cool. So whilst wait events will provide great insights when you're actually troubleshooting your performance issues, but to get a better value when you're actually taking, you'll actually get better value when you actually go in and sample your PGStat activity, right? It enables you to review your workloads and bottlenecks that you have actually led to that moment when you're actually starting to face your drop in performance. And you should also go in and sample other statistics views for SQL statements, your I/O activity, and the database as well. And while sampling wait events is helpful, don't undermine the value of logging critical events such as query waiting too long for a lock. And this can help augment the information that you already have capture through sampling activity and other wait events as well. And on the slide, you'll actually have a few parameters that I actually mentioned and views that will actually help you with this as well. And with that, we wanted to say thank you very much for attending our session.
Thanks, everyone. Thank you for attending this session. We are short of time. We can't take questions. But if you have any questions, feel free to grab us outside of this room. Or our emails are here. You can drop us a note. We'll be happy to have a conversation with you.